Um, as Angela's already said, I'm Will Hall-Lacey. And first I'm just going to take you through a bit of housekeeping before we get going. So this webinar will go for about an hour. The presentation should be around about 40 minutes and we'll have about 20 minutes allocated to questions. You will all be emailed a PDF of this presentation at the conclusion to the webinar. If at any time during the proceedings you would like to ask questions, please feel free to enter them in the box that's there for them. I'm currently planning to address the questions once we get to the end. I'll try and keep an eye on them as we go, but we'll see what happens. But yes, please type them as you go, that way at least I know what's going on. So, onto the presentation. I'm going to take you through a bit of an introduction as to what FAMLIT is and why we use it. We'll look at using FAMLIT for life cycle costs, using FAMLIT for marginal costs. Then we'll have two case studies, and I'll take you through some of the further work and leave you with where you can go to access more information on this. Even in 40 minutes, we're I guess only going to be scraping the surface a bit. But anyway, here we go. So it might be stating the obvious a little, but it's kind of the starting part for this work. I think we all know that roads wear, they deteriorate, and they require maintenance. Road managers are seeking to understand their roads better, and they're looking to minimize costs and maximize their treatment benefits and forecast the future needs of their road network. From the other side, I guess we have heavy vehicle operators who are seeking to run vehicles at higher mass limits to improve efficiency and return operating cost savings to them. But underneath all that, what does that actually do to the road? And what does that cost to maintain the road under these changing conditions? So that's where it was through all that we came up with the concept of developing FAMLIT. The origins of FAMLIT go back quite a long way, but recently through several projects with Austroads and the National Transport Commission, we've been developing this method to calculate costs and marginal cost. Trying to resolve that has involved a lot of challenges, so I'll try and take you through some of that in this webinar. So FAMLIT as a life cycle cost tool. FAMLIT can be broken down into a few different areas. We have inputs, we have some working models in the middle, and being a lifecycle costing tool, it outputs a cost at the end. Our inputs are our road description, and that includes things like its size, its type, its condition, its age, the climate that the road exists in. It also includes some model settings that might include calibration factors and unit costs and discount rates. And the third major input is our traffic loading, what the vehicle fleet is on the road and how it's loaded. And these three different inputs get put into the internal models within FAMLIT. And these models can be broken up into deterioration models in terms of strength and roughness, a works trigger model which determines the conditions under which you might do treatments, and a works effect model that will give you the effect of these treatments, including a cost. So this model runs on an annual basis over a 50-year life cycle, and at the end of that period it outputs a total cost for the life of that road. To look at it in a bit more detail, we can break it down into the road description. So FAMLIT can take multiple road sections at any one time. And each road requires attributes such as size, in terms of length and width, the climate, which is typically specified using the Thornton Moisture Index, pavement details such as strength and rutting, material coefficients and age, and surface characteristics such as the type and the roughness and the age of that surface. And each of the various road sections requires this information. Very closely tied to the road description and also required for each of the road sections are what I've entitled the model settings. And these include calibration coefficients for the various models, works intervention triggers, unit rates for the works, treatment details, things like maximum and minimum thickness of treatments and any limits that might be placed on them, and discount rate. The third input is the traffic loading. FAMLIT requires a fleet of representative vehicles to model the loading on the road. And the particular form of input requires us to approximate typical loads on the vehicles. These loads can come from a WIM analysis or from just making desktop assumptions. So here I've selected a quick fleet of vehicles, and we're going to look at the A123 in a bit of detail as an example. So I've just picked these loads out a bit at random as some approximate loads for the different axle groups on the truck. So if we have 5 tonne on the steer, 15 on the tandem drive, and 18 on the trail group. Each of these loads needs to be converted into an axle group SAR and then into summed up into a vehicle group SAR. So if you haven't used SARs before, understand where they come from, here's just a brief description for them. So a SAR is a measure used for road pavement wear. It's typically used by pavement engineers, and it's simply the axle group load divided by the reference load and then raised to a power, which is often called wear or a damage exponent. And this varies depending on the type of pavement. We'll be looking at a granular here, which gives us a damage exponent of 4. And the reference load, which is dependent on each of the different axle groups, and they're listed in this table down here. So for our steer axle, we take our load of 5 tonnes and divide it by a reference load of 5.4 and put it to the 4th power. For our tandem axle drive, we take our load of 15 tonnes and divide it by the reference load of 13.7 and raise it to the power of 4. And again, finally, for our tri-axle trail, it's our load of 18 tonnes divided by our reference load. It gives us another axle group SAR. And these are simply summed up to give us our total vehicle SAR. So this is required to be done for each vehicle in our input. This particular table is for our vehicles at GML, and if we come down here and look at our A123, the GML load's a bit higher, but this is the cell in which it would go into if we were calculating it using the loads on the previous sheet. I talked about the damage exponent, where we had a SAR 4 damage exponent for granular, a SAR 5 for asphaltic concrete, and a SAR 12 for the cement stabilised. So this is where each of those gets displayed in our input tables. From this table, we can then determine our traffic mix on each road simply using a vehicle count for each of those vehicles. So if we look at an example of a rigid 1-1 axle with a SAR 4 load, if we multiplied that through by the number of vehicles, so each vehicle has a SAR of 3, you multiply that by the 7 vehicles and we get a total of 21. So that would be a daily SAR load on the road and is what FAMLIT uses for its input. This becomes very powerful because it means that you can adapt the way that you would want to load your fleet and then take that fleet loading and apply it to any of your roads without having to change your original table. If you decided if there weren't any particular type of vehicle on a road, like an urban local access isn't going to have a road train on it, you can simply set that number of vehicles to 0 and it doesn't get included. Next we move to our deterioration model. The core of FAMLIT's deterioration model is the roughness deterioration model, which is an Ostrode's model. I don't want to spend any deep time looking at this or go into any detail except to show you that it's there. I'll have references at the end of the project if you want to look into that further. The key thing is that the roughness deterioration is a function of pavement age, of strength, of the traffic on the road, of rutting, of routine maintenance, and the environment. So I'll get that off the screen before it gets any more confusing. The works effect models within FAMLIT. FAMLIT has four different types of road maintenance that are available to be modelled. It has a routine maintenance, which is just an annual maintenance. It has reseals. It has overlays, or mill and replace, or resheet. Obviously that's depending on what the pavement type is, but they're all modelled in a very similar way and included together, and it includes reconstructions. For the recent work that we've been doing, we've configured FAMLIT to include reseals in the routine maintenance cost, so they don't actually get triggered separately, and we've set it up to not trigger reconstructions. But in making that decision, we've allowed overlay works we've allowed it to do very large overlays where it's required, more or less in place of those reconstructions. But FAMLIT does have the options to use all of these. The overlay works effect model I wanted to go into with some detail, as it was developed specifically for FAMLIT. The overlay works effect model converts the pavement into a two-layer model. So it takes the strength, it takes the CVR for the subgrade strength, and then determines what the thickness using the material coefficient is of that top layer. As the road deteriorates, it makes the assumption that the deterioration is just in that top layer. So as the strength is reduced, that layer is effectively reduced in thickness. And this is important because we are determining treatment thicknesses as one of the internal mechanisms in FAMLIT as part of the works effect model. So as the pavement deteriorates, it has an effective thickness reduction. And when a treatment is done, we need to determine, depending on how we configure that treatment, we can return the pavement to the same strength it was before, or the same material thickness. We can allow the pavement to be stronger than before, So where a mill and replace is required, we would set up a greater thickness this way by digging down into the subgrade more and applying a thicker pavement layer. Or if it was a resheet or an overlay, we could just add extra material on the top. It could also be configured to not necessarily return the pavement to the same strength as before, which would appear as a lower effective thickness. The cost that FAMLIT outputs is an equivalent annual uniform cost. You'll often see it abbreviated throughout this as an EAUC. This cost is the cost of all maintenance and treatments for the life of the project, but it's also discounted to present value, and it's annualized as well. So this graph on the left shows 50-year life of the road with annual maintenance treatments, and here at about 12 years we have a major rehabilitation cost. So all these costs are discounted to present value terms and are then annualized, so we end up with the same annual cost every year over the life of the project. So that's the life cycle model and how we get life cycle costs out of FAMLIT. But one of the things that has been increasingly important is marginal cost, and it's the primary reason that FAMLIT has been redeveloped. So I wanted to start by explaining what a marginal cost is. In traditional economic terms, a marginal cost is the increase in total cost of production as a result of producing one more unit of output. So if we want to think about that in road network terms, we might take the total cost of production as being equivalent to road authority maintenance cost and a unit of output as being freight, or more specifically in the way that we've done our modelling, axle mass. So this becomes the increase in road authority maintenance cost as a result of one more unit of axle mass. Part of the reason that this is quite important is that marginal costs are often used to set the price of an output. So I wanted to revisit this, or re-show you this life cycle model to keep that fresh in your head. So we've modelled a traffic loading scenario and we've outputted a total cost for that traffic loading scenario. But to take it to a marginal cost, we need to add a variable, and that variable is mass. So if we think about it this way, where we have a single mass that goes into FAMLIT and outputs a cost, and that cost can be plotted against its mass. And because we're varying mass, we'll add a second mass that will output a higher cost, and that again can be plotted with our mass against cost, and so on and so forth. As we increase the masses, we should be getting an increase in life cycle cost for that fleet at that mass. So the previous slide showed us the basic points of how we get that load wear relationship. Each cost has a load associated with it. And these loads can be specified either by the axle mass required that was used to get that loading scenario, or the overall SAR from that loading scenario. And you can see that in these two graphs down here. The one on the left has axle mass along the bottom, and the one on the right has a SAR value along the bottom. Both have cost on the vertical axis. To make these individual points more useful, we fit a function to them. So the axial mass graph has a function of a plus bx to the c to develop this power curve here. While the SAR, using SAR as our loading variable, we can develop a simple linear relationship. The slope of a regression curve at any point gives us the marginal cost. So taking the derivative of this, we end up with this slightly complex equation to give us the marginal cost, where we're using axial mass as the variable. If we're using SAR as the variable, we have the huge efficient. The marginal cost is a constant at any load. And so that's where using SAR as our loading variable becomes very, very useful. One of the things we had to grapple with when doing this work was something that's known as a marginal cost type, whether we were looking at short-run marginal cost or long-run marginal cost. So in economic terms, a short-run marginal cost maintains the same condition of the plant over the course of the life of the project. To convert this into road terms, we have assumed that for a short-run marginal cost, a treatment does not improve or increase the pavement strength past its original condition. The long-run marginal cost, in economic terms, allows for improvement in the plant over the life of the project. And so we've translated that as a treatment may increase the road strength past its original condition. We've managed the difference between these two by limiting our works effect model. As you saw earlier, there were options where the works effect model might increase the strength of the pavement, or it might set it where it was, or allow it to even not increase to its original strength. So we used the works effect models to determine whether it was a short-run or long-run project. In most cases, we found these options return similar results, but a question remains: which of these marginal cost modes is more appropriate to model the current practices on the road? Because ultimately that is what FAMLIT is trying to do. It's trying to model what's going on and the future needs of the road. So now I wanted to briefly take you into a couple of case studies. The first case study was part of work we did for Austroads and the NTC, and it was modelling a nationwide network. So the network setup was to have 17 road types across 3 different pavement types, being granular, asphaltic concrete and cement stabilised, with the idea of using these to represent the majority of the road network. Each of these 17 roads had 15 variations, and these variations came from 3 different climates. So we modelled the different climate regions using the Thornton Moisture Index, and we also modelled 5 different ages, or 5 different start ages for each of these pavements. This is to prevent some starting point problems that can occur. These pavement ages were grouped back together at the end of later in the analysis, so we never actually saw the different ages in the results. But the overall aim was to develop a marginal cost for a road that would apply to the road regardless of the age. Remember, we're trying to represent the entire network. The traffic loading consisted of 17 different vehicles. Typical vehicle loading was estimated by a room analysis, and the SAR tables were developed for each loading scenario. there was a loading scenario required for each of our 6 different axle groups. The way we set it up was that all axle groups would remain fixed at GML while one axle group changed. So we need a different scenario for each of those axle groups. And our loading scenarios vary from tear to well in excess of GML. I think when we were using 1 ton increments, we had in excess of 100 SAR tables as our inputs for that project. As I mentioned earlier, the traffic mix for each of the roads within this analysis was set using a simple vehicle count, or the vehicle numbers for each of those road types. A quick look at the results from this project. This graph is showing a comparison of how the different axle groups reacted to an increase in axle mass, which is why we loaded each of the axle groups separately. So on the vertical axis we have our cost, and on the horizontal axis we have an axle mass in excess of tear. And each of our different colours on this are our different axle groups. So as a single axle, single tyre axle group was loaded, that's the blue one here, we can see that it increases in cost very quickly. And as I mentioned earlier, the gradient is the marginal cost. And so we have an increase in marginal cost very quickly as well, which is what you would expect for such a small axle group when it gets loaded very heavily. At the opposite extreme, we have down the bottom here our quad axle dual tyre axle group, which as it gets loaded above tear, it increases very slowly. And also you can see that from the gradient that the marginal cost does not increase very quickly. And in between you can see all of these other axle groups. One that we often look at as an example is the tandem axle dual tyre, because it is a very common one, and that's this one here in blue, which, as you would expect, reacts somewhere in between the single axle single tyre and the quad axle dual tyre. If we take that same graph, looking at cost again on the vertical axis, but rather than axle mass, we look at SAR on the horizontal axis and compare those same costs for each of the different axle groups. We find that not only do we have a linear relationship within the axle group, but we have a linear relationship across all axle groups, which becomes, again, very powerful in terms of calculating marginal cost. We have a constant marginal cost for all of our axle groups at all of our axle loadings when we're looking at SAR values. While this is computationally more simple, SAR values can be hard to understand, which is why we have mostly been doing this work to include axle masses as well, so you have a reference for both. Excuse me just a moment. Next, I wanted to show a comparison of the way different road types react as the load is increased on each of them. So again, we have our cost on the vertical axis and our SARs on the bottom, on the horizontal axis. And each of the different colors on this graph is a different road type. Down at the bottom, it's almost a bit hard to decipher, but these purple ones are a rural access road. And at the top end here in blue, we have a granular freeway. In between, we also have a collector and 2 different arterials. Now, the key thing to note from this is the gradient of each of these lines for each of the roads, as that is what determines the marginal cost. As expected, as loads increase on the rural access road, it reacts very quickly because it is not a very strong pavement, and therefore we have a very high marginal cost. Moving up in strength, we have our rural collector and our rural arterials, both of which have a lower marginal cost, and our rural freeway, which has the lowest marginal cost. It is built the strongest, and therefore it should react least to that increase in load. And I've just put quickly quantified them down the bottom here in the table. Our rural freeway had a marginal cost of 0.8 cents per star kilometre, an annual marginal cost, versus our rural access, which had a much higher marginal cost. The other results I wanted to show you was a quick sensitivity analysis that looks at the way the model responds to, the FAMLIT model responds to changes in input parameters. So the input parameters that we changed were roughness progression coefficients, the starting strength of the road, and the different traffic levels. And what we were interested in is both the way it changed the total cost, but more importantly how it changed the marginal cost. Remember the gradient of this curve again. So in the middle of this graph we have our blue base case, and in reducing the roughness progression coefficient, as expected we had a reduction in total cost, but it made a relatively small change on the marginal cost. It's still running at roughly the same gradient as our base case. I'm going to skip over strength for a moment and go to traffic. Where we decreased traffic was this purple curve. We had again a slight change in total cost, but very little change in marginal cost. But as you would expect, as you reduce traffic, you reduce the cost. So we can see that it is reactive to increase and decrease in traffic. Coming back to strength, an increase in pavement strength brought about a slight decrease in total cost and a slight decrease in marginal cost. You can see that the gradient there is slightly lower, particularly up at the high end. And a decrease in strength produced both a higher cost and a higher marginal cost. So it was found that a decrease in strength was what this model was most sensitive to. So some conclusions from this case study. There are different and quantifiable marginal costs for each of the road types in terms of hierarchy and material. We found that our rural access and collector roads had the highest marginal cost, and our rural freeways and arterials had the lowest marginal cost. The short run and long run marginal costs that were presented are a good starting point, but further investigation is needed to confirm or improve these definitions, and that's part of the reason actually for doing these webinars, to let the people that are actually managing the roads know what we're working on and what we're doing, and to be able to improve those definitions. The sensitivity analysis showed that the pavement strength had the greatest impact on marginal cost. And we also found that variations in climate did not influence the marginal cost. So case study number 2 is really a microanalysis. It's for a project that I've only just completed. I don't know if the data's even got to the client yet, so I'm not actually going to be presenting any data, but I wanted to show you a quick concept. So the idea was to do a quick analysis of a few different road types to develop a quick ballpark comparison of what the marginal cost on these different roads were. So the setup for this project was to take 3 road types with 2 different pavement strengths, and that was just come about by a CBR change in each of those different 3 road types. To use 2 climates, we only used 1 age, and we simply used 6 SAR values. The downside of doing it this way was that I actually had to modify FAMLIT to be able to handle this particular case. But having done it once, it may be that we'll implement an option to do this in future versions. The advantages of this type of setup was that we were able to get relatively quick, it was relatively quick to set up, and it gave us a good clear ballpark comparison of how these different roads might react to increase in loading. The disadvantages were that there were a lot of assumptions required. Our pavement strengths were simply developed using material coefficients and thicknesses to calculate those strengths rather than having real data to input into that. So we end up with a less rigorous result, but it has a lot of potential for doing quick analyses. So the further work we're looking at doing with FAMLIT. FAMLIT is currently a beta version. It's been used for various projects, and it's kind of been a work in progress. Whenever something comes up, it might get tweaked or redeveloped for that particular project. I'm currently working on an Austroads project to refine the model and provide training to Austroads members on that. It basically means it gets cleaned up and we make it a bit more user-friendly and that sort of thing. So that's currently in progress, and we're coming towards the end of the first year on that. As with any modelling, our models are only as good as the data that goes in there. So we're always looking to have better data in terms of pavement strength and roughness and rutting, having better knowledge of the vehicle fleet in terms of number of vehicles, in terms of their type and their mass, and having all of this data in both the current state and time series. This enables you to set up a model far better and to calibrate it much more accurately. But all of that information also can be used in doing further research on things like FAMLIT and the deterioration models and works effect models within FAMLIT. We're always looking to do further research and improve those models so that something like FAMLIT that will output a life cycle cost can do that better. And as I mentioned earlier, we're always looking for collaboration with, I guess, with the people that are closest to what's going on the roads, the road managers, so that we can make all of this both more accurate to model, but also tailor it to road managers' needs. As I mentioned earlier, there is a huge lot within FAMLIT, far too much to cover in a half-hour, 40-minute presentation. So here are some places you can go to get some more information on it. The first one is an Austroads paper, and it is where the first case study came from as well, and it talks in depth about all the models within FAMLIT and how it was set up. It's available on the Austroads website. I think it is publicly available once you sign up to join Austroads or something like that. You sign up to get a username. I presented a paper at the ARB conference last year, and that paper is available online to be downloaded from the ARB website or using that link. I also co-wrote a paper that was presented at the Heavy Vehicle Conference in 2011. That paper was much more looking at marginal cost than looking at slightly isolated from FAMLIT, but that's also there and publicly available online. And if you're interested to see the way that some of these marginal costs and life cycle costs are being used at a higher level, you can look at an NTC paper there on heavy vehicle pricing, and that will give you some details about how it's planning to be used. Yeah, well, thank you for tuning into this webinar. If you would like any further information, please contact me. My details are right there. I'm going to grab a quick drink and then answer a couple of questions. So feel free to send through any more questions that you might have. All right then, I've got a couple of questions, so I'll start with them, but keep them coming. A question from Chris Herring. He's commented that FAMLIT sounds like a pavement management tool and has asked if it's based on HTM4. FAMLIT isn't really a pavement management tool. It's much more of a modelling tool specifically to just get out life cycle costs. It's not the sort of thing you would enter your entire road inventory into and use that to monitor when treatments are done. It's much more to enter a current state and future predict the way the road is going to behave. I'm not 100% sure what internal models HTM4 uses. FAMLIT isn't specifically based on HTM4, but certainly has some similarities. And it could actually contain some of the same deterioration models. I can't answer you whether they would be the same models, but generally they're used for different purposes, I think. Chris has also asked, I think what he's asking is, could it be used to look at the difference of a major fleet change from heavy vehicles? And that is essentially the way FAMLIT was originally developed, and you could compare two different traffic fleets and look at the output life cycle cost from that. I think, let me know if that answers your question on that. But yes, you could input two different fleets and get a life cycle cost out, so it could be used for checking that. Tyrone Tool has asked if there is a potential application for local councils. And the answer to that is there definitely is a potential for local councils. It's got potential for anyone that wants to do a life cycle model of a road, and councils are certainly not excluded when we talk about heavy vehicle operators wanting to run heavier trucks and that sort of thing. So it could be used anywhere that there is a marginal cost or life cycle cost application. We have done some work for local governments, and some of the roads that we have been modelling would have been local roads anyway. Peter's just asked if he can have a look at that second last slide with all the additional information on it. I can leave that up there for you, but if you're an attendee of this webinar, then we have your details and you'll all be emailed a PDF of this presentation. So I wouldn't worry about writing them down. They will all get sent out to you, and it should be much easier to get that way. Who else have we got here? I've got a question from Joshua. I'm not entirely sure how to pronounce your surname. Joshua Sisikis. He's asked, during the modelling process, do you consider cracking as one of the indices? The roughness deterioration model, I'm sorry, I left that out at the time, does include cracking as one of its inputs. It is a function of cracking as well. However, for the work that we've done to date, we've assumed that the pavement has been sufficiently well maintained to be sealed, and so the cracking has not been an issue. There is definitely potential to have that included, and there are variables for that. But in our current analysis, we haven't included cracking, but there is potential to in future. Another question from Tyrone. What variation in strength did the high and low represent? Excuse me for just a second. I'm going to mute the microphone for just a moment while I rustle some papers. Okay, back again. The change in pavement strength, it was very plus or minus 30% from the original strength. And we took that 30% both from the pavement and the subgrade. I had it written down, I just forgot to mention it, or I wasn't reading my notes when I went through the slide. Where's the next question? Just reading through a question from John Roberts here. He's asked, for local government application, is FAMLIT sensitive enough to assess the marginal cost from a change in forestry harvesting? I would think it would be. I haven't done a specific investigation in that area. But I suspect it would be. I suspect it would be. I'm guessing the change would in effect be from having next to no heavy vehicle traffic and mostly just having cars to having very highly intense, fairly heavily loaded traffic on that road. And I think it would be more than able to monitor that difference, as that is both a change in fleet and a change in axle masses on that road. So we would have to do a case study to answer that completely, but I think that that would certainly be possible, John. Coming to the end of the list of questions, well, that is the end of the list of questions I've got there. There's another one, just a second. Question from Mervyn Henderson. As marginal costs are sensitive to change in pavement strength, have you any thoughts on incorporating that variability into the model? We haven't specifically looked to incorporate a variability or a sensitivity with analysis within the model. However, the way the traffic input is set up, it's very easy to run that sensitivity or variability yourself. Because each road segment that you input has its entire road description unique to that road section, it's very easy to implement a duplicate section that has a different strength or a different roughness or a different age or a different cost or any of these things. So it's very easy to duplicate the network and simply make a mass variation in that to do a sensitivity analysis or look at the variability of one of these variables. So that's the way we did the sensitivity analysis that I've showed you, but I don't think we'd be looking at incorporated into the model. Excuse me just a second, I'm going to grab a drink. Okay, I've got another question here from Anil, I think is how you pronounce your name. How is the value of n determined for calculating SAR? That has not been a part of the work we've done for this project. That's been a fairly well accepted value or set of numbers or way of calculating SAR values for quite a long time. However, that said, there's always research going on for that. I believe it's been done through experimental tests. They've been working on that sort of stuff at our ALF testing facility here at ARB and looking to confirm them or improve them quite recently. But they may even go back to work that was done in the US. I can't actually give you a reference on that, but if you were to go to that first paper that I was talking about, the Ostrodes paper, I'm quite sure that somewhere in that there'll be a reference pointing to a good definitive source for that. But that's not been a part of work for this project. It's something that's happened through research over the years that I think is fairly well accepted in the industry these days. I've got another question here from Nelson, just asking, is the program available from ARB? What program is that? Is that a program of webinars or a program of research? I think we're coming to the end of all of these questions. Probably getting to the last chance to enter any more now, so send them through. We've got about another 5 minutes before we need to wrap up. Okay, we just had a whole lot more questions come through. There's a couple of questions here relating to whether the model is available for use. Currently, the model is not available for use because, as I said, it's very much in a development mode, and the code is all open, and there's no user manual written for it. And there's actually quite a lot of redundant code in there because it's been a model in development for quite a few years now. But like I said, there's a current Austroads project to clean that all up and make a publicly releasable make a public release version of FAMLIT. And what else was I going to say? And also to write a proper user manual and also provide training on it. So according to that program, the model should be finished this year, and in the subsequent years, the user manual and the user documentation and training will take place. So not yet, but soon. I'll very quickly try and deal with a question from John Roberts as the last question. We've only got a couple of minutes left. He's asked, how do you handle a heterogeneous road network with many pavement types, and how do you know when to change the SAR values? A heterogeneous road network, meaning that the whole network isn't of the same pavement type or same thickness or strength or even surface type. Basically, you would need to split the network into homogeneous sections. Sorry, there's actually two ways to do it, but I'll start with this one, into homogeneous sections, so that each section had much the same strength and had the same pavement type. Every different road that is entered, you can select a pavement type, you can select a pavement strength, whether it be asphaltic, concrete, granular, or cement stabilized. Those are all variables that can be inputted for each of the pavement types. And depending on what pavement type you select will depend on what SAR value you use. That's why you calculate all those SAR values, so they're all in the model and can be used for the appropriate roads when they're needed. An alternate method when calculating for an entire network is to set up representative road segments and then based on your actual network and use them and use the representative marginal costs, the representative life cycle costs, to apply to the entire network. Both of those are valid methods and have benefits going either way in looking at a heterogeneous network. I think that's it, and I think we're going to have to conclude there. If you have any other questions, then feel free to call or email me. I'm sure there's something I've missed that people will be interested in, but I'll have to leave it there for now. Thank you for listening and attending, and I look forward to hearing from any of you that have any more questions. Thanks very much.